Long before human beings understood what stars were, the night sky already looked permanent, a fixed ocean of light stretching endlessly above Earth, unchanged across generations, civilizations, entire empires rising and disappearing beneath it. But every star visible tonight is temporary. Some are already close to death. Others will survive for trillions of years longer than the sun. Yet every one of them is moving toward the same ending eventually, because the universe itself is not stable. It is changing constantly, slowly exhausting the energy that allows stars, galaxies, planets, and life to exist at all. And the strange part is that physicists can calculate what happens next with unsettling detail. The universe has a future history, not metaphorically, scientifically. According to modern physics, the cosmos passes through distinct eras, each one darker, colder, and more empty than the one before it. Right now, we live during the Stelliferous Era, the age of stars, a brief window where galaxies still glow and the universe still produces light naturally. But this era is temporary. In roughly 100 trillion years, the last true stars will burn out. After that, the universe enters something far stranger. Black holes become the dominant structures in existence. Entire galaxies collapse into darkness around them, and over spans of time so extreme that ordinary numbers stop being useful. Even the black holes themselves begin to disappear, particle by particle, radiation by radiation, until eventually the universe reaches a stage physicists call the dark era, a future so remote and empty that almost every structure that exists today will have vanished completely. But even that may not be the end. Some theories suggest space itself could eventually tear apart faster than light can hold matter together. Others suggest quantum mechanics allows entirely new universes to emerge long after ours becomes unrecognizable. And one possibility, taken seriously by several physicists, implies that consciousness itself may randomly reappear out of empty space, given enough time. The deeper scientists pushed these calculations, the stranger the future became. If space content like this is your thing, we've got plenty more. Subscribe, and you'll have a new documentary waiting for you next time you need one. Let's talk about what we actually know regarding the future history of the universe. Long before any telescope existed, the universe was already following rules, quiet ones, relentless ones. The future stretching ahead of us is not mythology or abstract philosophy. It emerges from four frameworks that have survived every serious attempt to break them. General relativity, which describes gravity and spacetime. Quantum mechanics, which governs the behavior of particles at the smallest scales. Thermodynamics, which tracks the flow of energy and entropy. And the Standard Model of particle physics, our most precise description of matter itself. When physicists Fred Adams and Greg Laughlin published The 5 Ages of the Universe in 1999, they organized the entire future history of existence into a sequence of eras, not poetic eras, physical ones, each defined by what kinds of objects can still exist and what kinds of energy remain available. The first is the primordial era, beginning with the Big Bang itself. The universe is violently hot, dense, and chaotic. Matter cannot settle into stable structures yet. Space is flooded with radiation. Only after hundreds of millions of years do the first stars finally ignite. Then comes the Stelliferous Era, the age of stars. This is our era. Galaxies shine, planets form, chemistry becomes rich enough for oceans, atmospheres, and life. This era begins roughly 1 million years after the Big Bang and continues until around 100 trillion years. After that arrives the Degenerate Era. All stars are dead, only their remnants remain, white dwarfs, neutron stars, brown dwarfs, and drifting black holes. The universe becomes colder, darker, and vastly quieter. This age stretches from roughly 100 trillion years to 10 undecillion years. Beyond it waits the black hole era. Almost everything else has vanished. Black holes dominate the cosmos, isolated inside expanding darkness. This era lasts until around a Google years, a 1 followed by 100 zeros, and after even black holes disappear, the universe enters the dark era. No stars, no galaxies, no large structures at all. Only sparse particles wandering through expanding emptiness for timescales language barely accommodates. To navigate spans this extreme, physicists stop counting years normally. Instead, they use logarithmic time, measuring existence in powers of 10. Each step is not an addition, but a multiplication. 1 million becomes 1 billion, then 1 trillion, then numbers so enormous they stop feeling numerical and start feeling geological. Underneath all of it sits entropy, simple in definition, devastating in consequence. Entropy measures how energy spreads out and becomes unusable. Ordered systems decay into disordered ones. Hot things cool, structures break down, differences flatten, and according to the second law of thermodynamics, this process only moves one way, which makes our position in the timeline strangely fragile. The Stelliferous Era lasts around 100 trillion years. The universe today is approximately 13.8 billion years old. We are less than 0.02% through the age of stars. Almost all stellar history still lies ahead. But even now, the long fading has already begun. Across the observable universe, stars are turning darkness into structure. Every glowing point in the sky represents matter resisting collapse for a little longer, balancing gravity against the outward pressure of nuclear fusion. Right now, this balance exists on a scale almost impossible to picture. Roughly 200 billion trillion stars are currently burning across the visible cosmos, scattered through about 2 trillion galaxies. There are likely more stars than grains of sand on every beach and desert on Earth combined, repeated several times over. This is the universe near its peak complexity, not symbolically, physically. Galaxies still contain cold hydrogen gas, the raw material from which stars form. Gravity pulls this gas inward until pressure and temperature become high enough for hydrogen atoms to fuse into helium, releasing energy. That process lights the stars, but the supply is shrinking. Around 10 billion years ago, the universe was producing new stars at nearly 30 times the current rate. Astronomers measure this decline through something called redshift, the stretching of light caused by cosmic expansion. The peak arrived around a period known as redshift 2, and since then the long slowdown has continued. Galaxies are consuming themselves gradually, quietly. Most stars alive today are red dwarfs, small stars with low mass and dim light. They make up roughly 70% of all stars in existence. Because they burn fuel extremely slowly, some will survive for up to 10 trillion years. Our Sun belongs to a rarer category called G-type stars, middle-sized stars with lifespans around 10 billion years. About half of the Sun's lifetime is already gone. Then there are blue giants and supergiants, enormous stars, violent ones. Their cores burn so intensely that they exhaust their fuel in only a few million years, vanishing almost as quickly as they appear. Inside the Milky Way alone, astronomers estimate there are between 100 billion and 400 billion stars. The uncertainty exists because we live inside the galaxy itself, buried within dusty spiral arms that block our view across large regions of the disk. But even galaxies are temporary arrangements. The Milky Way is already absorbing smaller satellite galaxies through gravity, slowly pulling them apart star by star. In about 4.5 billion years, it will collide with the Andromeda Galaxy. Each contains hundreds of billions of stars, yet direct stellar collisions will remain extremely rare because stars are separated by immense distances relative to their size. Instead, the galaxies themselves will distort, their gas clouds compressed into brilliant new waves of star formation. Eventually, the merged system, sometimes called Milky Meta, will settle into a swollen elliptical galaxy with fading structure and little remaining gas, and after roughly 100 trillion years, the final red dwarfs will exhaust their hydrogen fuel. The age of stars will end. The night sky you know exists during a temporary window, the brightest and most intricate chapter the universe will ever experience. Every second, the sun converts roughly 600 million tons of hydrogen into helium deep inside its core. That fusion process has continued for about 4.6 billion years, holding gravity in balance through outward pressure and heat. But the balance is temporary. The sun is a middle aged star, and about half of its usable hydrogen fuel is already gone. The first signs of change arrive slowly. In roughly 1 billion years, the sun's luminosity, its total energy output, will rise by around 10%. That sounds minor. It is not. Earth's climate depends on extremely narrow temperature boundaries, and this gradual brightening will trigger a runaway greenhouse effect similar to the one that transformed Venus. The oceans begin evaporating into the atmosphere. Water vapor traps additional heat. Surface temperatures climb higher still. Complex life disappears long before the sun itself changes shape. But the deeper transformation begins around 5 billion years from now, when hydrogen fusion in the sun's core finally stops. Without outward fusion pressure supporting it, the core contracts under gravity and grows hotter. Fusion continues temporarily in a shell surrounding the collapsing core, releasing enormous amounts of energy into the outer layers above it. The sun swells outward. Its radius may expand to nearly 200 times its current size, stretching outward toward Earth's orbit. Mercury disappears first, then Venus. Earth may survive physically because the sun loses mass during this phase, causing our orbit to drift slightly outward. But survival is a technicality. The surface will already be scorched, airless, and molten. Inside the expanding star, something extraordinary happens. As the core contracts further, temperatures eventually climb above 100 million degrees Celsius. Helium nuclei begin fusing into carbon in an event called the helium flash. Despite the name, no explosion becomes visible outside the sun. The event is trapped deep within the core itself. Yet during those few violent minutes, the sun releases more energy internally than it currently emits across a million years. The instability settles briefly. Helium fusion continues, producing carbon and oxygen at the center. But helium fuel is limited too. When it runs out, the core contracts again, while the outer layers drift farther into space. The sun begins shedding itself. Gas streams outward over thousands of years, forming an expanding shell called a planetary nebula. The name is misleading. Planetary nebulae have nothing to do with planets. Early astronomers simply thought they resembled faint planetary disks through small telescopes. In reality, they are enormous clouds of ionized gas glowing under intense ultraviolet radiation from the exposed stellar core. At the center remains the final remnant, a white dwarf. About half the sun's original mass survives, compressed into a sphere roughly the size of Earth. A teaspoon of its material would weigh around 15 tons on Earth. No fusion continues there. The white dwarf only radiates stored heat into surrounding darkness. cooling gradually across trillions of years. Long after Earth becomes a dead mineral fragment circling empty space, the sun's white dwarf will still remain faintly warm. Some stars spend billions of years fading slowly into silence. Others die in catastrophes visible across entire galaxies. The difference begins with mass. A star more than roughly 8 times heavier than the Sun lives fast, burns violently, and ends in collapse. Inside these massive stars, fusion becomes layered. Hydrogen burns into helium near the outer regions. Deeper down, helium fuses into carbon, then carbon into oxygen, oxygen into neon, neon into silicon. The star develops concentric shells of fusion, stacked inward like layers inside an onion, each hotter and denser than the one above it. But each stage grows shorter. Hydrogen fusion can continue for millions of years. Helium lasts hundreds of thousands. Carbon survives perhaps centuries. Silicon fusion, the final stage before collapse, continues for roughly one day. Then the core fills with iron. Iron is fatal to stars because it cannot release energy through fusion. Fusing iron consumes energy instead of producing it. The outward pressure that once resisted gravity suddenly disappears, and the core loses the ability to support its own weight. Collapse begins instantly. In less than a second, the iron core falls inward from a diameter comparable to Earth down to a sphere only about 20 kilometers wide. Atomic structure itself fails. Electrons and protons are crushed together into neutrons. The collapse accelerates until nuclear forces abruptly resist further compression. The core rebounds. A shock wave tears outward through the infalling layers above it, blasting the star apart in a core collapse supernova. For a brief period, a single exploding star can outshine every other star in its host galaxy combined. We witnessed one ourselves in 1987. Supernova 1987, A appeared in the Large Magellanic Cloud, about 168,000 light years away. It became visible to the naked eye from Earth, the closest observed supernova since the time of Johannes Kepler in 1604. Neutrino detectors deep underground even recorded the flood of subatomic particles released from the collapsing core hours before the visible explosion reached us. These explosions are not merely destructive, they are creative. The golden jewelry, the uranium inside rocks, the nickel, copper, silver, and iron moving through your bloodstream were forged inside stars like these and scattered outward by supernova shock waves. Every massive star enriches the galaxy chemically before it dies. What remains afterward depends on mass again. Many leave behind neutron stars, objects containing between 1 and 2 solar masses, compressed into a sphere barely 20 kilometers across. A teaspoon of neutron star material would weigh around 10 million tons on Earth. Some neutron stars rotate extraordinarily fast. These are pulsars, spinning remnants that emit narrow beams of radio waves from their magnetic poles. In 1967, Jocelyn Bell Burnell discovered the first pulsar because its signals arrived with such precise regularity that researchers briefly considered the possibility of artificial origin. Others become magnetars, neutron stars with magnetic fields reaching roughly 1 quadrillion Gauss. Earth's magnetic field measures only about half a Gauss by comparison. A magnetar passing halfway between Earth and the Moon could disrupt electronics across the entire planet. But the most massive stars collapse further still. Above roughly 20 solar masses, gravity may overwhelm everything completely, and the core vanishes directly into a black hole, sometimes without any visible explosion at all. If you could compress the sun without changing its mass, shrinking it down to a sphere only 6 kilometers across, gravity would become so extreme that not even light could escape. The result would not be a hole punched into space. It would be an object, dense, physical, defined by mass, rotation, and sometimes electric charge. A black hole forms when gravity overwhelms every known force resisting collapse. Its defining boundary is called the event horizon, the distance from the center where escape velocity reaches the speed of light. Escape velocity simply means the speed required to break free from gravity. Beyond the horizon, no possible path leads outward because nothing travels faster than light itself. But the horizon is strangely intangible. It has no surface you could touch, no texture, no solid boundary. It is a geometric feature woven into space-time, a dividing line between regions that can still communicate with the universe and regions forever cut off from it. Inside that boundary, the geometry of reality changes profoundly. In ordinary life, moving forward through time feels unavoidable, while movement through space remains optional. Inside a black hole, those roles effectively reverse. Approaching the singularity, the infinitely compressed center predicted by general relativity, becomes as inevitable as tomorrow morning. There is no standing still there. Black holes appear across a vast range of sizes. The smallest known category contains stellar mass black holes, formed from collapsed massive stars and ranging from roughly 5 to 100 solar masses. Above them may exist intermediate mass black holes, objects containing hundreds or even hundreds of thousands of solar masses. Astronomers still debate exactly how these form. Some may emerge from collisions between smaller black holes, while others could originate from enormous primordial gas clouds collapsing directly in the early universe. Then come the supermassive black holes. Almost every large galaxy appears to contain one at its center. The Milky Way hosts Sagittarius A star, a supermassive black hole containing about 4 million solar masses. In 2022, the Event Horizon Telescope collaboration released the first direct image of it, reconstructing the glowing ring of hot gas swirling around the horizon. Some are vastly larger still. The quasar, known as TON 618, contains an estimated 66 billion solar masses. Its event horizon extends wider than the orbit of Pluto around the Sunday. Entire solar systems could disappear inside it without approaching the center. Near black holes, gravity does not pull evenly. It changes sharply across short distances. This creates tidal forces, differences in gravitational strength between one part of an object and another. A human falling toward a stellar mass black hole would experience spaghettification, stretched into a long strand as feet accelerate faster than the head. But perception near the horizon becomes deeply strange. To a distant observer, anything falling inward appears to slow down due to gravitational time dilation, the slowing of time in strong gravity. The object fades, reddens, and seems frozen forever near the edge. Yet for the falling observer, nothing unusual occurs while crossing the horizon itself. And despite their reputation, black holes are not cosmic vacuum cleaners. If the sun were instantly replaced by a black hole with identical mass, Earth's orbit would remain almost unchanged. We would freeze in darkness, but gravity would continue guiding us along the same path through space. Eventually, there comes a night with no sunrise anywhere. The final red dwarf exhausts the last of its hydrogen fuel after surviving for nearly 100 trillion years. No new stars ignite after it. Fusion, the process that powered galaxies across almost the entire visible history of the cosmos, finally fades away. The Stelliferous Era ends not with an explosion, but with exhaustion. What remains is a colder population of objects drifting through widening darkness. White dwarfs still exist in enormous numbers. These compact stellar remnants continue radiating stored heat into space, though only faintly now. Over trillions upon trillions of years, they cool further, shifting from white to red, then eventually toward black, becoming nearly invisible against the surrounding void. Neutron stars persist too, dense, tiny, ancient. Some still rotate slowly after unimaginable spans of time, though most have long since fallen silent. Black holes remain scattered throughout the cosmos as well, from collapsed stellar remnants to the supermassive giants once anchored at galactic centers. There are also brown dwarfs, objects too small to sustain hydrogen fusion when they formed. They spent the entire age of stars as dim failures and now cool steadily toward temperatures barely above absolute zero. Planets survive longer than many stars do. Over billions of gravitational encounters, countless worlds are ejected from their systems entirely. These rogue planets drift alone between galaxies, frozen and lightless. Thin gas clouds still wander through interstellar space too, but they are stretched so far apart that gravity can no longer compress them into fresh stars. But the darkness is not perfectly still. Some white dwarfs orbit companion stars closely enough to steal material from them. Gas accumulates gradually on the dwarf surface until it exceeds the Chandrasekhar limit, the maximum mass a white dwarf can support against gravity. That limit, calculated by Subramanian Chandrasekhar in 1930, while traveling from India to England at only 19 years old, is about 1.4 times the mass of the Sunday. Beyond that threshold, collapse becomes unstoppable. The white dwarf detonates as a Type 1, a supernova, briefly flooding surrounding space with intense light before vanishing forever. During the Degenerate Era, these explosions become rare, isolated flashes inside a universe otherwise gone dark. Meanwhile, galaxies themselves slowly dissolve. This process is called galactic evaporation. Stars, remnants, and planets constantly exchange tiny amounts of energy during gravitational interactions. Over enough time, some objects gain sufficient velocity to escape entirely, not violently, statistically, like molecules gradually leaking from an open container. Around 10 quintillion years from now, most galaxies will have lost the majority of their contents this way. What remains near their centers will slowly spiral inward towards supermassive black holes. By 1 nonillion years, structure on the scale of galaxies has largely disappeared. White dwarfs, neutron stars, rogue planets, and black holes drift at distances so immense that encounters become almost non-existent. Ordinary matter still survives here. But whether it survives forever depends on a single unanswered question inside particle physics. Can a proton die? At the center of every atom sits a tiny cluster of particles called the nucleus. Inside that nucleus are protons and neutrons, packed together by the strong nuclear force, the interaction responsible for holding atomic matter intact. Everything solid you have ever known depends on their stability. Mountains, oceans, bones, planets, dead stars drifting through the far future. All of them are built from protons. For a long time, physicists assumed protons were eternal. But modern particle physics leaves open another possibility. Stability is not the same thing as permanence. Certain theories suggest that given enough time, even protons may eventually decay into lighter particles. These ideas emerge from grand unified theories, often shortened to GUTs. They attempt to merge three of nature's fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force, into a single framework operating at extremely high energies. In many of these models, Protons are not perfectly stable objects. They simply survive for absurdly long times. The predicted half-life, meaning the average time required for half of a collection of protons to decay, ranges from roughly 1 nonillion to 1 undecillion years in the simplest versions of these theories. When a proton decays, it likely transforms into a positron, the antimatter counterpart of the electron, and a neutral pion. The pion then disintegrates almost instantly into gamma ray photons. Matter becomes radiation. Structure dissolves into light. So physicists have searched for evidence. Deep beneath Mount Ikeno in Japan sits the Super Kamiokande detector, a cylindrical chamber containing 50,000 tons of ultra-pure water buried about 1 kilometer underground inside a zinc mine. More than 11,000 photomultiplier tubes line the walls, each designed to detect tiny flashes of light produced when high-energy particles move through the water. The detector has operated since 1996. It has never seen proton decay. That absence matters. Each year without detection pushes the lower limit on proton lifetime higher. Current observations rule out the simplest grand unified theories for the most common decay pathways, placing the proton lifetime above roughly 10 undecillion years. More complex models remain possible, but the universe is offering no easy answers. Still, if proton decay does occur, the consequences are absolute. White dwarfs slowly evaporate, particle by particle. Neutron stars dissolve from within. Rogue planets lose their atomic structure. Carbon, oxygen, silicon, iron, every familiar element eventually breaks apart across unimaginable spans of time. The degenerate era ends because matter itself stops being durable. But if protons never decay, the future remains strange anyway. Quantum tunneling, a verified effect where particles pass through barriers they should not classically cross, will still rearrange matter over sufficiently long durations. Stability only becomes statistical. Nothing remains fixed forever. Either outcome leads toward the same destination. By the close of the degenerate era, ordinary matter no longer dominates the cosmos. The universe entering the next age is populated increasingly by only one kind of long-lived structure, objects whose gravity traps even light itself. There comes a period when the universe contains almost nothing familiar. No stars burn, no planets orbit, no dust clouds drift through galaxies, because galaxies themselves have largely dissolved. If proton decay has occurred, even atoms are gone. What remains are black holes, sparse radiation, and scattered elementary particles moving through expanding emptiness. The black hole era begins around 10 duodecillion years after the Big Bang and stretches toward a googol years, a 1 followed by 100 zeros. Black holes are now the last major structures in existence. Each one exists like an isolated island of gravity surrounded by incomprehensible darkness. The expansion of space continues separating them farther apart over time. They do not gather into new systems or rebuild lost structure. Every black hole becomes increasingly alone, drifting through a universe that grows colder and thinner with every passing age. For a long time, physicists believed black holes were eternal. But in 1974, Stephen Hawking discovered something astonishing while combining quantum mechanics with general relativity. Black holes are not completely black, they emit radiation. The mechanism emerges from quantum fluctuations near the event horizon. Empty space is never truly empty. Particle and antiparticle pairs constantly appear and annihilate each other at microscopic scales. Near a black hole, gravity can separate these pairs before they disappear again. One particle falls inward while the other escapes into space. The escaping particle carries away energy. That energy must come from the black hole itself, which means the black hole slowly loses mass over time. This process is called Hawking radiation, and it transforms black holes from permanent objects into temporary ones, but temporary on scales beyond ordinary language. A stellar mass black hole takes roughly 1 vigintillion years to evaporate completely. Supermassive black holes survive vastly longer, some enduring up to a Google years before disappearing. The larger the black hole, the colder it is and the slower it evaporates. Right now, black holes absorb more energy than they emit because the universe is still relatively warm. A stellar mass black hole radiates at only about 60 billionths of a Kelvin, far colder than the current cosmic microwave background temperature of 2.7 Kelvin. Only after the universe cools further does evaporation dominate. As a black hole shrinks, its temperature rises. Radiation intensifies. The evaporation process accelerates faster and faster near the end. After surviving for timescales so immense that entire cosmic eras seem brief by comparison, the final moments unfold violently. The black hole erupts in a burst of high energy radiation. In fractions of a second, it releases energy comparable to millions of nuclear weapons. Gamma rays flood outward into a universe almost entirely empty of matter. There are no nearby stars to illuminate, no planets to strike, no observers waiting in the dark. Then the black hole is gone. Its mass has returned to the cosmos as diffuse radiation spreading across expanding space. One by one, over unimaginable expanses of time, every remaining black hole follows the same fate until the last giant evaporates into silence. Imagine throwing a book into a black hole. Every page falls inward. Every atom, every microscopic detail, describing the arrangement of ink, paper, temperature, and motion, disappears beyond the horizon. The black hole grows slightly heavier, then eventually evaporates across immense spans of time through Hawking radiation. What happens to the information describing the book itself? This question became one of the deepest crises in modern physics because quantum mechanics depends on a principle called information conservation. In simple terms, the complete quantum state of a system can never be truly erased. If you possessed enough knowledge, the laws of quantum theory imply that past states could, in principle, be reconstructed from future ones. But Hawking's original calculations created a contradiction. The radiation emitted by black holes appeared purely thermal, meaning random and featureless, containing no encoded record of what originally fell inside. A black hole formed from books, planets, or stars would evaporate into identical radiation, regardless of its history. If that conclusion is correct, information vanishes permanently, not hidden, destroyed. That would violate one of the central foundations of quantum mechanics, placing general relativity and quantum theory into direct conflict. The two most successful frameworks in physics would become mathematically incompatible under extreme conditions. The argument that followed reshaped theoretical physics for decades. Stephen Hawking and Kip Thorne became convinced information truly disappeared inside evaporating black holes. Physicist John Preskill disagreed, arguing quantum mechanics must survive intact. They even made a formal wager, with an encyclopedia offered as the prize. In 2004, Hawking conceded the bet. He accepted that information is probably preserved somehow, though the exact mechanism remained uncertain. The paradox did not disappear, it deepened. One major proposal emerged from physicists Gerard Hooft and Leonard Susskind. They developed the holographic principle. the idea that information inside a volume of space may actually be encoded on its boundary surface. Like a hologram storing three-dimensional information on a two-dimensional sheet, the event horizon itself could preserve the record of everything crossing it. Under this picture, black holes never truly erase information. They scramble it beyond practical recovery. But new complications appeared. In 2016, Hawking, Malcolm Perry, and Andrew Strominger proposed that black holes may store information through subtle quantum imprints called soft hair. These are patterns left by extremely low energy photons around the event horizon. The concept remains controversial, and many physicists doubt it fully resolves the problem. Then came the firewall paradox. In 2012, Ahmed Almheri, Donald Merolf, Joseph Polchinski, and James Sully argued that preserving information may require the event horizon to become violently energetic. Instead of crossing smoothly, an infalling observer would strike a wall of intense radiation called a firewall. That directly contradicts general relativity, which predicts nothing unusual at the horizon itself. So, the contradiction remains alive. Quantum mechanics insists information survives. General relativity insists space-time near the horizon remains smooth. Black holes appear to demand both simultaneously, yet current physics cannot fully reconcile them. Somewhere inside this paradox may lie the missing theory of quantum gravity, the framework physicists still do not possess. After the final black hole evaporates, the universe does not collapse or explode. It simply thins out further. The last burst of Hawking radiation expands into surrounding space, its wavelengths stretched longer and longer by cosmic expansion until even that fading signal becomes undetectable. Nothing large remains anymore. No stars, no planets, no black holes, no galaxies suspended across intergalactic darkness. The universe now consists mostly of photons, neutrinos, electrons, and positrons drifting through an expanding void whose scale has become almost meaningless. Temperature still exists, but barely. The cosmos hovers fractions of a fraction of a degree above absolute zero, the lowest possible temperature in physics, equal to negative 273.15 degrees Celsius. At absolute zero, ordinary thermal motion effectively ceases. Particles no longer jostle with usable energy. Heat no longer flows meaningfully from one place to another. Expansion continues regardless. Every surviving particle grows more isolated over time because the average distance between particles keeps increasing forever. Even encounters between individual electrons become extraordinarily rare. Space itself stretches faster than anything can rebuild structure. This state is called heat death, sometimes known as the Big Freeze. The phrase sounds dramatic, but its meaning is technical. Heat death describes maximum entropy, the condition where usable energy gradients no longer exist. An energy gradient simply means a difference that allows work to happen: hot versus cold, dense versus diffuse, high pressure versus low pressure. Every engine, every living organism, every star relies on gradients. In the dark era, those differences disappear. Entropy reaches its highest accessible state. In thermodynamics, entropy measures the number of microscopic arrangements capable of producing the same large-scale condition. Maximum entropy means maximum disorder, where energy has spread so evenly that no organized process can continue. The second law of thermodynamics drives all of this forward. It states that entropy increases in a closed system over time, not usually, not statistically on average, fundamentally. 19th century physicist Ludwig Boltzmann understood the implications more deeply than almost anyone alive at the time. He developed the mathematical foundation of entropy and recognized that the universe itself appeared to be winding irreversibly toward equilibrium. Historical accounts suggest the realization haunted him personally for years. Even time changes meaning here. The arrow of time, your sense that past and future differ, emerges from entropy increasing. We remember lower entropy states and move toward higher ones. But in a maximum entropy universe, no thermodynamic distinction separates before from after because nothing changes enough to define direction. There are no meaningful clocks in the dark era. A clock requires motion, transitions, repeating cycles. All processes depend on usable energy differences, and those differences have faded into uniformity. The universe still exists physically, but activity has nearly vanished from it. But quantum mechanics refuses perfect stillness. Even inside this vast equilibrium, empty space itself remains restless at the smallest scales, fluctuating with tiny probabilistic events that never fully disappear. In ordinary life, empty space appears inactive. A vacuum seems silent and motionless, a place where nothing happens. But quantum mechanics describes something stranger. Even perfect emptiness contains fluctuating fields and temporary particles appearing and vanishing continuously at microscopic scales. The dark era never becomes completely still because space itself cannot remain perfectly quiet. One of the clearest examples of this behavior is quantum tunneling, a phenomenon already verified countless times in laboratories. Tunneling allows particles to cross energy barriers they should not classically overcome. Nuclear fusion inside stars depends on it. So do the transistors inside every computer chip ever built. At human scales, tunneling appears subtle. Across the enormous stretches of the dark era, it becomes transformative. If proton decay never occurs, some atomic nuclei may survive into these distant epochs. Iron is especially important because it represents one of the lowest energy stable nuclei in nature. Yet even iron is not completely immune to quantum effects. Over time scales, around 10 raised to the power of 1,500 years, surviving nuclei could slowly rearrange themselves into even more stable configurations through tunneling processes alone. Matter keeps changing, even in near-perfect darkness. Dense stellar remnants face stranger possibilities still. Quantum mechanics permits extremely improbable events as long as they are not forbidden outright. A white dwarf, given enough time, could spontaneously tunnel into a black hole without any supernova or collision occurring first. The estimated waiting time for such an event is almost beyond language, roughly 10 raised to the power of 10 raised to the power of 76 years. That is not merely a large number. It is a hierarchy of numbers stacked beyond ordinary intuition. Yet quantum theory allows it. These newly formed black holes would not remain forever either. They would evaporate through Hawking radiation exactly like earlier black holes did, releasing faint energy back into surrounding space. Tiny echoes of the black hole era would continue appearing sporadically, generated only through random quantum fluctuations. Then comes an even more unsettling idea. In the late 19th century, mathematician Henri Poincaré proved a theorem in statistical mechanics now called Poincaré recurrence. It states that any finite system with bounded energy will eventually return arbitrarily close to a previous configuration if given sufficient time. Applied cosmologically, the implication becomes extraordinary. If the observable universe is finite and ergodic, meaning it explores all accessible states over time, then arrangements resembling earlier cosmic structures may eventually reappear spontaneously. Entire configurations of matter, stars, galaxies, perhaps even states similar to our present universe, could recur through random fluctuations alone. The estimated recurrence time reaches roughly 10 raised to the power of 10 raised to the power of 118 years. These numbers are so extreme that words like eternity stop functioning properly around them. But the implication matters more than the arithmetic. Heat death may not represent a final ending in the absolute sense. The Dark Era could instead resemble an unimaginably vast waiting period where possibility never entirely disappears. Even after everything familiar has faded, quantum mechanics leaves the universe restless beneath the silence. In a universe lasting forever, even absurdity becomes statistically possible. That realization emerged from the work of Ludwig Boltzmann, the physicist who helped uncover the statistical nature of entropy. Boltzmann understood that random fluctuations inside a thermal system can temporarily create ordered structures by chance alone. Normally, these fluctuations are tiny, a brief concentration of energy here, a particle arrangement there. But over infinite time, probability loses its intuition. Anything not forbidden eventually happens. Inside the vast equilibrium of the Dark Era, quantum fluctuations continue endlessly. Given enough time, particles could randomly arrange themselves into increasingly complex configurations. A molecule, a crystal, a dead planet, even something vastly stranger, a Boltzmann brain. The term describes a fully self-aware mind, assembled spontaneously from random fluctuations, not metaphorically, literally, a functioning consciousness appearing briefly inside chaos, complete with memories, identity, sensory impressions, and awareness, before dissolving back into disorder moments later. The probability is unimaginably small, but infinite time changes the mathematics. Events so improbable they would never occur across trillions of ordinary universes become inevitable if the Dark Era persists long enough. The cosmos keeps rolling the dice forever. And this creates a disturbing statistical problem. If the universe remains in a high entropy state for immense durations, Boltzmann brains would eventually outnumber all biological observers who evolved naturally during the age of stars. There were only finitely many humans, animals, and civilizations across cosmic history, but random fluctuations in an eternal thermal universe could produce endless artificial observers. That means a randomly selected conscious mind would most likely not be biological at all. It would be a fluctuation, a temporary arrangement of particles with fabricated memories of parents, childhoods, planets, telescopes, conversations, and histories that never actually happened. The brain would awaken, believing itself embedded inside a coherent universe, because those false memories would be part of the fluctuation itself. It would have no way to know otherwise. This idea sounds philosophical, almost fictional, but cosmologists discuss it seriously because it exposes weaknesses in certain models of the universe. Physicists, including Sean Carroll, Andreas Albrecht, and Lorenzo Sorbo, have argued that a successful cosmological theory should avoid producing overwhelming numbers of Boltzmann brains. Otherwise, the theory predicts that observers like us are statistically abnormal. That becomes a problem for science itself. If most conscious observers are random fluctuations carrying false memories, then trusting observation and reasoning becomes deeply unstable. The issue stops being only cosmological and becomes epistemological, meaning it questions how knowledge itself can be trusted. Boltzmann brains represent a collision between probability and consciousness. The universe becomes so old and so random that awareness itself emerges accidentally from noise, not through evolution, not through stars or planets, through statistical inevitability alone. But perhaps the strangest part is this: the argument only works because the laws of physics permit matter to organize into minds at all. Somewhere between the first stars and the final darkness, the universe discovered a way to become aware of itself, whether briefly through biology or fleetingly through chance. So far, the future has unfolded through fading. Stars burned out, matter decayed, black holes evaporated, entropy slowly flattened the universe into stillness. But there is another possibility in modern cosmology, one far more violent. The universe may not freeze to death. It may tear itself apart. This scenario is called the Big Rip, and it depends entirely on the nature of dark energy, the unknown phenomenon driving the accelerated expansion of the cosmos. Observations currently show that dark energy makes up roughly 68% of the total energy content of the observable universe. It dominates cosmic evolution, yet physicists still do not know what it actually is. The simplest explanation treats dark energy as a cosmological constant, a fixed energy built into space itself. Under that model, expansion accelerates steadily forever, but never becomes destructive on local scales. But there is a more extreme possibility. Dark energy may instead be a form of phantom energy, where the pressure associated with space becomes even more negative over time. Physicists describe this using a quantity called the equation of state parameter, written as W. If W equals -1 exactly, dark energy behaves like a stable cosmological constant. But if W drops below -1, expansion becomes runaway. The more space expands, the stronger dark energy becomes. In a phantom energy universe, the acceleration eventually overwhelms every binding force in existence. Gravity fails first, then electromagnetism. Finally, even nuclear forces collapse. The destruction arrives in stages. About 200 million years before the final moment, galaxy clusters become gravitationally unbound. Entire collections of galaxies drift apart because gravity can no longer compete against expanding space. Roughly 60 million years later, individual galaxies themselves unravel. Stars lose their orbits. Spiral structures dissolve. Darkness widens between every remaining object. Around 3 months before the end, the solar system breaks apart. Earth drifts away from the sun as gravity fails across planetary scales. 30 minutes before the final instant, Earth itself is torn into fragments. Then the destruction descends below matter. Less than a billionth of a trillionth of a second before the end, atoms are ripped apart. Electrons separate from nuclei because electromagnetic attraction no longer holds them together. At the final moment, protons and neutrons themselves disintegrate as the strong nuclear force finally loses against the expansion of spacetime. Every scale fails simultaneously. Space does not merely contain destruction in this model. Space becomes the destruction. Current observational evidence does not favor this outcome. Measurements of distant supernovae, galaxy distributions, and the cosmic microwave background remain consistent with W equal to -1, supporting the cosmological constant model instead. But uncertainty remains. Projects such as the Dark Energy Spectroscopic Instrument, known as DESI, continue refining these measurements by mapping millions of galaxies across cosmic history. A small shift in the value of W would completely alter the universe's final fate. The Big Rip remains scientifically possible because we still do not understand the dominant ingredient of the cosmos itself. And if phantom energy proves real, the universe ends not in darkness or silence, but in the simultaneous destruction of every structure that ever existed. Near the end of the 20th century, astronomers believed they understood the broad direction of cosmic history. The universe was expanding from the Big Bang, and gravity should gradually slow that expansion over time. Galaxies ought to be pulling against the outward motion like weights tied to an expanding fabric. Then the measurements arrived. In 1998, two separate research teams began studying distant Type 1, a supernovae, exploding white dwarfs bright enough to serve as cosmic distance markers. Saul Perlmutter led the Supernova Cosmology Project. Brian Schmidt and Adam Rees led the High Z Supernova Search Team. Their goal seemed straightforward. They wanted to measure how quickly gravity was decelerating the expansion of the universe, but the supernovae appeared dimmer and farther away than expected. The only explanation fitting the data was astonishing. Expansion was speeding up. The universe was not slowing down under gravity. Space itself was accelerating outward. Galaxies were moving apart faster with time, not slower. The discovery overturned one of the central assumptions of cosmology almost overnight. Perlmutter, Schmidt, and Rees later received the 2011 Nobel Prize in Physics for the discovery, widely regarded as one of the most surprising scientific findings in decades. Whatever drives this acceleration became known as dark energy. It is not the same thing as dark matter. Dark matter behaves gravitationally and clumps around galaxies, helping hold cosmic structures together. Dark energy does the opposite. It appears smooth and evenly distributed through space, exerting a repulsive effect across enormous distances. The leading explanation traces back unexpectedly to Albert Einstein. When Einstein first developed general relativity, he added an extra term to his equations called the cosmological constant, represented by the Greek letter lambda. He introduced it to force the universe into a static state because expansion had not yet been discovered observationally. Then Edwin Hubble revealed the universe was expanding after all. Einstein reportedly called the cosmological constant his greatest blunder and abandoned it, but modern observations revived the idea decades later because a constant energy built into empty space matches many properties of dark energy remarkably well. Yet this creates another problem, perhaps even worse. Quantum field theory predicts that empty space should possess vacuum energy. Tiny fluctuations present even in perfect emptiness. But when physicists calculate the expected energy density of the vacuum, the result exceeds the observed value of dark energy by roughly 120 orders of magnitude. It is the largest mismatch between theory and observation in all of science. Not a minor discrepancy, not a rounding issue, a catastrophe of mathematics. Some physicists propose alternatives instead, including quintessence, a dynamic energy field changing over time and space, rather than remaining constant everywhere. Different models predict slightly different expansion histories, and ongoing observations continue testing them against reality. But no explanation has won decisively. The future of the cosmos depends entirely on which answer proves correct. Heat death, the Big Rip, endless expansion, perhaps something stranger, all emerge from the same unresolved mystery. Most of the universe is controlled by something we still cannot identify. Not every model of the future ends with endless expansion. Some cosmologists have imagined the opposite fate, a universe that eventually stops growing outward and begins falling back inward under its own gravity. This scenario is called the Big Crunch. For it to happen, dark energy would need to change behavior dramatically. The accelerated expansion we observe today would have to weaken, vanish, or reverse sign entirely. Gravity would then regain dominance across cosmic scales, slowly overcoming the outward motion left from the Big Bang. Current observations strongly disfavor this possibility. But cosmology has a long history of overturned certainties. Entire models, once treated as settled, later collapsed under new evidence. So the Big Crunch remains scientifically discussable, even if it no longer leads most predictions. If contraction begins, the sequence unfolds gradually at first. Expansion slows, galaxies stop receding, then motion reverses. Across billions of years, distant galaxies begin approaching each other again. Their light shifts blueward as wavelengths compress instead of stretch. The night sky grows increasingly crowded and bright as ancient structures return toward proximity. Temperature rises everywhere. The cosmic microwave background, currently only 2.7 Kelvin above absolute zero, slowly heats as radiation compresses into smaller volumes of space. Over immense stretches of time, the entire universe becomes hotter and denser. Stars struggle to survive inside the growing radiation bath. Eventually, they cannot. Long before natural stellar death occurs, increasing temperatures ionize atoms apart. Electrons separate from nuclei. Matter dissolves into plasma. As contraction continues, even atomic nuclei themselves break apart under extreme conditions. The universe begins resembling its earliest moments again. Density climbs toward incomprehensible extremes where known physics breaks down. General relativity predicts a singularity, a point of infinite density and curvature similar to the mathematical beginning of the Big Bang itself. But some physicists suspect collapse may not end there. Loop quantum cosmology, a framework applying quantum gravity corrections to spacetime, proposes that quantum effects create a repulsive pressure at extremely high densities. Instead of forming a final singularity, the collapsing universe rebounds outward. A bounce replaces the ending. Under this model, cosmic history becomes cyclic. Expansion leads to contraction. Contraction leads to another expansion. The universe may pass through endless sequences of births and deaths without absolute beginning or final termination. Roger Penrose proposed a different cyclic idea called conformal cyclic cosmology. In his framework, the remote future of a heat-death universe becomes mathematically equivalent to a new Big Bang because scale itself loses meaning at both extremes. Without massive particles remaining, there is no physical ruler left to distinguish immense size from tiny size. Penrose and collaborators have claimed to identify possible traces of previous cosmic cycles inside the cosmic microwave background. They describe circular features called Hawking points, potential fingerprints from ancient universes preceding our own. Most cosmologists remain unconvinced by the evidence. But Penrose is not an outsider figure. He is one of the most influential mathematical physicists of the modern era, and his cyclic universe remains a serious scientific proposal rather than pseudoscience. The possibility remains open that endings are not endings at all, only transitions between cosmic chapters separated by unimaginable time. Every ending we have explored so far unfolds across immense stretches of time. Trillions of years pass. Black holes evaporate slowly. Entropy spreads gradually through expanding space. But there is another possibility hidden much deeper inside modern physics. The universe may not survive long enough to reach any of those futures. Vacuum decay begins with the Higgs field, an invisible field filling all of space. Fundamental particles interact with this field to acquire mass. Without it, electrons would remain massless, atoms could not form, and chemistry as we know it would never exist. The Higgs field appears stable today, but stable may not mean permanent. Physicists describe the field as sitting inside an energy landscape. Imagine a ball resting inside a valley. It may appear settled and motionless, yet a deeper valley could still exist elsewhere. If so, the current state is only metastable, meaning temporarily stable rather than absolutely secure. This possibility emerged after measurements of the Higgs boson at the Large Hadron Collider suggested a troubling result. Based on the measured Higgs mass, around 125 gigaelectron volts, and the mass of the top quark, our vacuum may not represent the lowest possible energy state available to nature. A deeper vacuum may exist beneath reality itself. Quantum tunneling could eventually trigger a transition into this lower energy state. Somewhere in space, without warning, a tiny bubble of true vacuum could spontaneously form. Inside that bubble, the Higgs field would settle into its deeper minimum, changing the laws of physics completely. The bubble wall would expand outward at the speed of light. Nothing could outrun it. No signal could arrive beforehand because any warning would travel at light speed too, reaching observers simultaneously with the boundary itself. There would be no countdown, no visible approach across the sky. One moment the universe exists normally, the next it does not. Inside the bubble, particle masses would change instantly. Electrons, quarks, and fundamental forces would behave differently. Atoms could no longer remain stable. Chemistry would vanish. Stars, planets, biological structures, and every organized form of matter would become impossible. Vacuum decay does not destroy the universe in the ordinary sense. It replaces it. The underlying fabric of reality shifts into a different state where everything familiar ceases to function. Not burned away, not shattered, simply rendered incompatible with the new laws governing existence. Current calculations suggest this metastable state, if real, would survive vastly longer than the present age of the universe. There is no evidence that vacuum decay is imminent. But the conclusion remains sensitive to precise particle measurements, especially the exact mass of the top quark, which physicists continue refining experimentally. A slight adjustment could move the universe from metastable to genuinely stable. Stephen Hawking discussed this possibility in his final writings, noting that sufficiently extreme energies might theoretically trigger vacuum decay locally. Human technology remains nowhere near capable of producing such conditions. But nature itself may not require assistance. Somewhere beyond observation, the quantum field's underlying reality may already be waiting at the edge of a deeper valley. All the endings we have explored so far share one hidden assumption. They treat our universe as the entire stage, the complete arena where reality unfolds. But several major ideas in modern physics suggest something far larger. Our universe may be only one region among many. The first proposal emerges from cosmic inflation, the brief period of exponential expansion believed to have occurred during the universe's earliest moments. Inflation explains why space appears remarkably smooth and flat across enormous distances. According to some versions of the theory, inflation never completely stops everywhere at once. It continues eternally in parts of space. While inflation ends locally in one region, creating a universe like ours, other regions continue inflating and producing new bubble universes endlessly. Each bubble may contain different physical constants, different particle masses, perhaps even different numbers of spatial dimensions. This framework is called the inflationary multiverse. Physicists Alan Guth and Andre Linde helped develop many of its central ideas. Under this picture, our observable universe becomes one pocket inside a far larger cosmic structure beyond direct observation. Another proposal comes from string theory. String theory attempts to unify quantum mechanics and gravity by describing fundamental particles as tiny, vibrating strings rather than point like objects. But the mathematics permits an enormous number of stable solutions, each corresponding to different physical laws and constants. This collection of possibilities is called the string landscape. Current estimates suggest roughly 10 raised to the power of 500 distinct vacuum states may exist. Each could represent a different universe with unique properties. Some would expand too quickly for galaxies to form, others might collapse instantly. Many would never permit chemistry or stable matter. We appear to inhabit one of the rare regions where complexity becomes possible. Then there is a very different kind of multiverse entirely. In 1957, physicist Hugh Everett proposed the many worlds interpretation of quantum mechanics. Instead of wave functions collapsing during measurements, Everett argued that every possible quantum outcome actually occurs. Reality branches continuously into parallel histories whenever quantum events happen. Every alternative outcome exists somewhere. In one branch, a particle moves left, in another, right. These branching universes are not separated across space, but across quantum history itself, forming an ever-multiplying tree of realities. These proposals do not imply one another. The inflationary multiverse, the string landscape, and many worlds arise from different physics and face different criticisms. Yet they share a common challenge. None can currently be tested in ways fully satisfying traditional standards of scientific falsifiability. Their predictions are either inaccessible by definition or so subtle that existing instruments cannot detect them reliably. But their implications remain profound. If any version of the multiverse is correct, then the death of our universe is not the end of everything. It is only a local event inside a larger structure, continuing beyond us indefinitely. Our universe may vanish, while countless others persist untouched. The collapse of stars, the evaporation of black holes, even heat death itself could be cosmically insignificant beyond our own bubble of reality, as small and unnoticed as the death of a single cell inside a living organism, far too large for the cell to comprehend. Long before stars existed, the universe glowed everywhere at once, not with starlight or galaxies, but with heat. In its earliest stages, the cosmos was filled with a dense plasma of free electrons and atomic nuclei, moving through temperatures so extreme that light itself could not travel freely. Photons scattered constantly from charged particles, trapped inside a brilliant fog. Then the universe cooled enough for something new to happen. About 380,000 years after the Big Bang, electrons finally slowed enough to bind with protons and form neutral hydrogen atoms. This moment is called recombination. Once atoms formed, light could move across space without scattering endlessly from free charges. The universe became transparent for the first time. The radiation released during that transition still exists today. We call it the cosmic microwave background, or CMB, the oldest light humanity can observe. Its temperature now measures only 2.725 Kelvin above absolute zero. Satellites, including COBE in 1992, WMAP between 2001 and 2010, and the Planck mission between 2009 and 2013 mapped this faint radiation with extraordinary precision. The CMB appears almost uniform across the sky, but not perfectly. Tiny fluctuations exist at the level of roughly 1 part in 100,000. These minute temperature differences represent ancient density variations originating during the inflationary epoch when quantum fluctuations were stretched across cosmic scales. Those wrinkles changed everything. Gravity amplified them slowly across billions of years. Slightly denser regions gathered more matter, eventually forming galaxies, clusters, and the vast filamentary web spanning the observable universe. Every large structure we see today emerged from those microscopic irregularities embedded inside the CMB. In a sense, galaxies are frozen sound waves from the early universe. But the cosmic microwave background itself continues changing too. As space expands, the wavelengths of its photons stretch outward. Over 13.8 billion years, the radiation has shifted from visible and infrared light into microwaves. It will keep stretching forever. By the end of the Stelliferous Era, the CMB will cool to billionths of a Kelvin. During the black hole era, its wavelengths will exceed the size of observable regions themselves. Eventually, the radiation becomes effectively undetectable. Future civilizations may never know it existed. Imagine observers arising 100 trillion years from now around the last red dwarfs. They would see no detectable microwave background, no evidence of cosmic expansion, no distant galaxies beyond their local gravitational neighborhood. The clues revealing the Big Bang would be gone. Such observers might conclude the universe was static and eternal because all observable evidence of a beginning would have faded beyond reach. Cosmology itself would become almost impossible. We happen to live during a narrow interval when the universe still carries visible traces of its own birth. The oldest light remains detectable. The earliest structures remain readable. When we study the cosmic microwave background, we are looking at the universe's first surviving memory, still hanging silently across the sky after nearly 14 billion years. There are galaxies we can see tonight that we can never reach. Their light still arrives faithfully across billions of years, crossing expanding space to touch our telescopes. But the galaxies themselves are already gone from us in every practical sense, carried outward by cosmic expansion faster than any future signal could ever travel. The observable universe is not the whole universe. It is only the region whose light has had enough time to arrive since the Big Bang. Today, that sphere extends roughly 46 billion light-years in every direction, containing an estimated 2 trillion galaxies spread across the cosmic web. But visibility is not the same as accessibility. Beyond a certain distance lies the cosmic event horizon, a boundary created not by darkness or matter, but by expansion itself. That horizon currently sits about 16 billion light-years away. Galaxies beyond it are receding so quickly that even light emitted toward us today will never overcome the stretching of space. We are seeing their past, not their present. Some of the galaxies visible in deep field images have already crossed permanently beyond our reach. Their ancient light continues traveling toward us because it began its journey long ago, when the universe was smaller and the distances were shorter. But no message we send now will ever arrive there. As cosmic expansion accelerates, more galaxies slip across this boundary every moment. They are not exploding or vanishing. Space between us simply grows too rapidly for information to bridge the gap. The universe is slowly erasing itself from view. In roughly 150 billion years, nearly every galaxy outside the local group will disappear beyond the horizon entirely. The local group, our gravitationally bound neighborhood of around 50 galaxies, including the Milky Way, Andromeda, and Triangulum, will remain intact because gravity overpowers expansion at those scales. Everything beyond it will fade away. The future night sky will look profoundly different from ours. Observers living during that era would see only the stars of the merged Milky galaxy and a small population of satellite galaxies orbiting nearby. The immense lattice of clusters and filaments stretching across today's cosmos would be invisible. No distant galaxies, no expanding universe, no detectable cosmic structure beyond the local system. Future astronomers may never discover the Big Bang at all. Without remote galaxies to compare against, there would be no measurable Hubble expansion. Without the cosmic microwave background, already stretched beyond detectability by then, there would be no surviving thermal echo of the early universe. Their cosmos would appear static and isolated. They might conclude the universe consists only of their galaxy, surrounded by eternal darkness. The deeper truth would remain hidden beyond horizons they could never cross and evidence they could never recover. We happen to exist during a narrow interval when the universe is still readable. The galaxies remain visible. The ancient radiation still glows faintly overhead. Expansion can still be measured. But even now, while we speak of the cosmos as though it were stable and permanent, parts of it are already slipping away forever. Every path we have followed eventually bends toward the same boundary. Whether we trace the fading of stars, the evaporation of black holes, or the expansion of empty space, physics eventually carries us to moments where its own equations stop giving reliable answers. The future has those boundaries, but so does the past. The Big Bang is one of them. General relativity, Einstein's theory describing gravity as the curvature of spacetime, predicts that the observable universe began in a state of zero size and effectively infinite density. This condition is called a singularity, a point where mathematical quantities diverge beyond physical meaning. At that point, the equations fail. The problem is not merely technical. A singularity signals that the theory itself has reached the edge of its applicability. General relativity can describe the universe expanding after the Big Bang with extraordinary precision. It successfully predicts gravitational lensing, black holes, and the expansion of galaxies across cosmic distances. But it cannot describe the beginning itself. The instant we approach the earliest fraction of a second, quantum effects become dominant, and relativity no longer works alone. We need quantum gravity, a theory uniting quantum mechanics with space-time geometry. No complete version yet exists, so physics faces a difficult silence there. Stephen Hawking and James Hartle proposed one possible way around this silence in the 1980s. Their no-boundary proposal suggested that time itself emerged with the Big Bang. In this model, the universe has no temporal edge requiring a prior moment. There may have been no before. Hawking often compared the question to asking, what lies south of the South Pole? The geography itself breaks the question. South ceases to exist beyond that point. In the same way, time may cease to have meaning before the universe began. The cosmos would then be self-contained, not created inside time, but creating time as part of its own structure. Cause and effect would emerge only after the beginning, not before it. But other physicists approached the problem differently. Alexander Vilenkin proposed that the universe may have quantum tunneled into existence from nothing. Quantum tunneling, already observed in laboratories and stars, allows systems to cross barriers they classically should not pass. In this framework, nothing means no space, no time, and no matter. A tiny closed universe could spontaneously appear through quantum processes, then inflate into the expanding cosmos we inhabit now. The mathematics permits such solutions. But the underlying physics remains incomplete because quantum gravity itself remains unfinished. So the most honest answer is still uncertainty. We do not know whether anything preceded the Big Bang. We do not know whether time existed beforehand, whether multiple universes existed beyond ours, or whether the question itself is physically meaningful. But this uncertainty is not evidence of failure. It marks the horizon where observation ends, and deeper understanding has not yet arrived. The beginning of the universe and the end of the universe mirror each other in this way, both waiting beyond the farthest reach of current physics. Biology discovered something strange about life on Earth. Complexity did not appear all at once. It accumulated gradually through variation, inheritance, and selection across immense spans of time. Species best suited to reproduction became more common, while less successful forms disappeared into evolutionary history. Lee Smolin wondered whether universes might behave the same way. In the 1990s, while working on problems in quantum gravity and cosmology, Smolin proposed an idea called cosmological natural selection. It remains one of the most unusual attempts to explain why the laws of physics appear so finely balanced for structure and complexity. The proposal begins inside black holes. According to general relativity, matter collapsing beyond a certain density forms a singularity, a region where space-time curvature becomes effectively infinite and known physics breaks down. Smolin suggested that these singularities may not be true endings. They may be beginnings instead. In his framework, each black hole gives birth to a new expanding universe hidden beyond its event horizon. The child universe disconnects causally from the parent, meaning no information can travel back between them once formation occurs. Each new universe inherits physical laws similar to its parent, but not identical. The constants governing gravity, particle masses, and nuclear forces would shift slightly with each cosmic birth. Small mutations introduced during the transition through the singularity. Most universes produced this way might be sterile, expanding too quickly for galaxies to form or collapsing before stars can ignite. Some would produce stars efficiently, and stars above certain masses create black holes when they die. That means universes better at forming massive stars generate more black holes, and therefore more offspring universes. The process resembles evolution by natural selection. Over countless generations, universes with physical constants favoring black hole production would become statistically dominant across the larger multiverse population. Complexity would not require deliberate design. It would emerge through cosmic reproduction and selection pressure. Our own universe appears strangely compatible with this idea. The strengths of the fundamental forces sit within narrow ranges, allowing long-lived stars, heavy element formation, and gravitational collapse into black holes. Slight changes to the strong nuclear force or neutron mass could dramatically reduce black hole formation altogether. Smolin argued this may not be coincidence. Unlike many multiverse proposals, cosmological natural selection also attempts something rare. It makes predictions. If our universe has been optimized through selection, then small changes to physical constants should generally reduce black hole production rather than increase it. That makes the theory scientifically vulnerable. A confirmed discovery showing altered constants would create more black holes could undermine the framework directly. This separates Smolin's proposal from ideas that remain permanently beyond observational testing. But the emotional implication runs deeper than the mathematics. Every black hole scattered across cosmic history may contain an entirely separate expanding universe, evolving under different physical laws. Our own universe may itself exist inside a black hole, formed within another parent cosmos, whose stars and galaxies vanished long before ours began. In that picture, endings are never entirely endings. A collapsing star becomes a doorway, a black hole becomes a cradle, and what looks from our side like destruction may appear from somewhere else as the first moment of creation. A clock measures motion, a pendulum swings, a crystal vibrates, a planet circles a star. We experience time through change so constantly that the two concepts seem inseparable. But as physics pushed deeper beneath ordinary experience, something unsettling emerged. The equations themselves do not care which direction time moves. Isaac Newton's laws of motion work perfectly well whether events unfold forward or backward. Maxwell's equations describing electromagnetism behave the same way. So do Einstein's equations for relativity and Schrödinger's equation for quantum mechanics. Run them in reverse, and they still function. A shattered glass reassembling itself violates common experience, yet the microscopic laws governing the atoms themselves mostly allow it. Nothing in the deepest equations clearly marks yesterday as different from tomorrow, except one law. The second law of thermodynamics states that entropy increases in closed systems. Entropy, the number of microscopic arrangements producing the same large-scale state, naturally trends upward over time. Ordered energy spreads out. Structure becomes less structured. This gives time its direction. We remember the past rather than the future because the past contained lower entropy. The arrow of time may not be woven into the foundations of reality itself. It may emerge from thermodynamics, from the statistical behavior of enormous numbers of particles. Without entropy increase, time loses orientation. Some physicists take this idea even further. The block universe model, favored by many working in relativity, proposes that past, present, and future all coexist simultaneously inside a four-dimensional space-time structure. Nothing flows in this picture. Every moment already exists. Your childhood, this conversation, and the final fading of stars occupy different regions of the same geometric structure. The sensation of moving through time would then arise from consciousness itself, not from the universe dynamically advancing. There would be no universal now. Einstein hinted at this repeatedly in his later writings. After the death of his friend Michel Besso in 1955, Einstein wrote that the distinction between past, present, and future is only a stubbornly persistent illusion. But other approaches attempt to rebuild time from deeper physics. Carlo Rovelli, one of the leading researchers in quantum gravity, proposed the thermal time hypothesis. In this framework, time emerges from thermodynamic relationships between systems. The direction of time is simply the direction in which entropy increases. No entropy gradient, no meaningful time. That possibility becomes deeply important in the far future universe. During the dark era, matter has dissolved, black holes have evaporated, and usable energy gradients have vanished. Nothing changes in ways capable of supporting clocks, memory, or irreversible processes. The universe approaches thermal equilibrium, and equilibrium erases distinction. Without change, before and after become physically empty categories. A universe at maximum entropy may not merely be quiet. It may exist in a condition where time itself has dissolved into symmetry, not because some cosmic clock stopped ticking, but because clocks only make sense in worlds where something still happens. The question of what occurs after the universe dies may therefore contain a hidden contradiction, asking for a later moment in a reality where later no longer has meaning at all. Try to imagine the age of the universe not as history, but as scale. The cosmos around us is approximately 13.8 billion years old. Written scientifically, that becomes 1.38 times 10 to the power of 10 years. Even spoken aloud, the number barely feels connected to ordinary life. Human minds were not built for spans like this, but compared to the future ahead, the current universe is still astonishingly young. The Stelliferous Era, the long age of shining stars, is expected to last roughly 100 trillion years before the final red dwarfs exhaust their hydrogen fuel. We are standing near the beginning of that era. Our position falls at roughly 0.014% of the total lifespan of stars. If the entire age of stars were compressed into a single calendar year, humanity would appear within the opening hour of January 1st. Almost everything is still ahead. Recorded human civilization reaches back around 5,000 years. Agriculture, cities, writing, mathematics, astronomy, philosophy, every empire and scientific discovery together occupy only a tiny fraction of cosmic history. Compared to the universe's current age, civilization spans roughly 3.6 times 10 to the power of -7, less than a millionth. Imagine stretching the history of the universe across a distance of 1 meter. The entire span of human civilization would occupy less than the width of a human hair pressed against the edge of that line. And yet these numbers do not describe irrelevance. They describe timing. We exist during the era of maximum visible complexity. Galaxies still glow with active star formation. Heavy elements remain abundant enough for rocky planets and organic chemistry. Temperatures across vast regions of space still permit liquid water and stable atmospheres. The universe is still alive with structure. The cosmic microwave background continues drifting through space at about 2.725 Kelvin, still carrying information from the universe's earliest transparent moment. We can detect it because the cosmos remains young enough for that ancient radiation to survive within observable wavelengths. We are close enough to the beginning to remember it. The large-scale cosmic web also remains visible. Galaxy clusters still trace enormous filaments across hundreds of millions of light years, allowing us to map the architecture of the observable universe directly. And distant galaxies still shine toward us. With modern telescopes, we can observe light emitted more than 13 billion years ago, effectively looking backward through nearly the entire history of cosmic expansion. But this window will not remain open. In roughly 150 billion years, nearly every galaxy beyond the local group will disappear beyond the cosmic horizon. The microwave background will stretch into wavelengths too enormous to detect. Expansion itself will become observationally invisible. Future civilizations may inherit a far poorer universe. They could emerge intelligent and curious while lacking access to the evidence needed to reconstruct cosmic origins. Much of what we now understand would become permanently unreachable. So this is not merely the age in which we happen to exist. It may be the best observational era the universe will ever offer. Every night sky you have ever seen belonged to a cosmos still filled with light, memory, and visible history. And against impossible odds, you arrived in time to witness it. At some unknowably distant moment, a final star will still remain. Not a bright blue giant or a sun like ours, but a red dwarf, small and stubborn. Perhaps only 1/10 the mass of the Sunday red dwarfs consume hydrogen with extraordinary efficiency. They burn slowly, dimly, conserving their fuel across spans of time longer than the current age of the universe, by thousands of times. This last star will exist alone. Its nearest neighboring stars may already be separated by distances requiring hundreds of thousands of years for light to cross. Galaxies will have thinned. Stellar populations will have evaporated outward through gravitational interactions until only scattered remnants drift across expanding darkness. The final red dwarf keeps burning anyway. For trillions upon trillions of years, it will continue converting hydrogen into helium inside a tiny convecting core. Its surface glow will remain faint, deep red against a sky almost entirely empty of visible structure. Then the fusion rate falls. The remaining hydrogen becomes too sparse to sustain pressure against gravity. The star cools gradually, shrinking toward darkness. No explosion marks its death. No nebula expands outward. The last true star simply fades until it becomes another cold remnant drifting through the Degenerate Era. But isolated flashes still interrupt the dark. Somewhere, perhaps after intervals longer than entire galactic civilizations once lasted, a white dwarf, locked in a binary system, slowly steals gas from a companion object. Matter accumulates over unimaginable ages until the dwarf crosses the Chandrasekhar limit, approximately 1.4 solar masses. Then, thermonuclear runaway begins instantly. Carbon fusion ignites across the entire star almost simultaneously. A Type Ia supernova erupts, releasing more energy in days than ordinary stars emit across millions of years. For a brief time, the dead universe lights again. There are no planets nearby with oceans reflecting the blast. No astronomers record the event. The explosion expands into silence because physics requires it to happen, not because anyone survives to witness it. Far later, even neutron stars begin surrendering their motion. A final pulsar rotates through darkness, sweeping weak radio beams across empty space like a lighthouse without a coastline. Each rotation bleeds energy away. Gradually, the pulses slow. Seconds stretch into minutes, then hours. Eventually, the beam stops entirely. The neutron star becomes a cold sphere suspended in blackness. After that, only black holes remain as meaningful structures in the cosmos. Then comes the final Hawking burst. Perhaps the last surviving black hole began as something like TON 618, a supermassive giant containing 66 billion solar masses. Across 10 to the power of 100 years, Hawking radiation slowly strips its mass away particle by particle. As it shrinks, it grows hotter. The final instant arrives violently. Gamma rays erupt outward in a brief release of enormous energy, the last concentrated flash the universe will ever produce. The radiation expands into emptiness with almost nothing left to absorb it. Then even that fades. Photons drift apart, electrons drift apart, neutrinos drift apart. Expansion continues, stretching the distances between particles without limit. The universe still exists mathematically, but events no longer occur in any meaningful sense. There is still something instead of nothing, but almost nothing happens forever. We can finally return to the question that has followed us through every era of this journey. What actually happens after the universe ends? Physics gives an answer that is both astonishingly detailed and deeply incomplete. Some parts are mapped with extraordinary confidence. Others dissolve into uncertainty the farther forward we move. The first transition is comparatively clear. The Stelliferous Era ends when the last stars stop burning. Red dwarfs, the slowest and longest-lived stars in existence, eventually exhaust their hydrogen after around 100 trillion years. Star formation ceases permanently because the supply of cold hydrogen gas has been consumed or scattered beyond recovery. After that, the universe enters the Degenerate Era. Galaxies become graveyards of remnants. White dwarfs cool across trillions of years. Neutron stars drift through darkness. Brown dwarfs radiate away their remaining heat. Black holes continue orbiting inside the fading ruins of former galaxies. But even those structures are temporary. If protons decay, ordinary matter slowly dissolves into lighter particles and radiation. Entire planets disappear atom by atom. White dwarfs evaporate from within. Neutron stars lose the particles holding them together. Matter itself ceases to exist in the familiar sense. If protons do not decay, the outcome changes only in detail. Quantum tunneling, the same process allowing particles to cross forbidden energy barriers, gradually rearranges surviving matter anyway. Over incomprehensible spans of time, atoms reorganize toward lower energy states or collapse into new black holes through rare quantum events. Either path leads toward the same destination. The black hole era begins once black holes become the dominant surviving structures in the cosmos. For stretches reaching up to 10 to the power of 100 years, they persist alone in expanding darkness, slowly evaporating through Hawking radiation. Then the final black hole dies. After its last burst of radiation disperses, the universe enters the dark era, the longest and quietest phase of cosmic history. Photons continue traveling, neutrinos continue drifting. Space continues expanding, but organized structure is gone. This is heat death. A universe in thermal equilibrium contains no usable energy gradients. Without differences in temperature or density, no work can occur. No stars ignite. No chemistry unfolds. No clocks function meaningfully because change itself has nearly vanished. The universe technically still exists, but almost nothing happens. Beyond that point, physics becomes less certain. If the cosmos is finite and obeys the right statistical conditions, Poincaré recurrence suggests that random fluctuations could eventually recreate previous states, including arrangements resembling our universe today. The timescales involved are almost impossible to express. Estimates reach numbers like 10 raised to the power of 10 raised to the power of 118 years. Whether such recurrences represent meaningful rebirths is no longer clearly a physics question. Other proposals remain open: cyclic universes, quantum gravity bounces, multiverse scenarios, new vacuum states, additional dimensions. Each offers possible continuations beyond heat death, but none have been experimentally confirmed. So the most honest answer remains surprisingly simple. For roughly the next 10 raised to the power of 100 years, physics describes the universe's future with remarkable precision. Beyond that horizon, the equations grow uncertain, and our maps begin to fade into speculation. At the farthest edge of cosmic time, science does not end with certainty. It ends with humility. Long before telescopes measured cosmic expansion or satellites mapped the microwave background, people already sensed that permanence was an illusion. Civilizations rose and vanished. Mountains eroded. Languages disappeared. Even the night sky changed slowly above human history. But modern cosmology transformed that ancient intuition into something far larger and more precise. It revealed that the universe itself has a lifespan, not metaphorically, physically. By the 19th century, physicists had already begun confronting the implications of thermodynamics. Entropy, the tendency for usable energy to become increasingly dispersed and unavailable, implied that the cosmos was slowly winding down toward equilibrium. The phrase heat death entered scientific discussion not as poetry, but as mathematics. The emotional weight of that realization reached far beyond physics departments. In 1903, the philosopher Bertrand Russell wrote that all human achievements were destined for extinction in the eventual death of the solar system. Art, science, memory, language, every triumph of civilization would disappear. Yet Russell did not conclude that meaning was impossible. He argued the opposite. Human beings could still create value consciously, even inside a temporary universe. That idea continued through later generations of thinkers. The physicist Brian Greene, writing more than a century later in Until the End of Time, described meaning itself as part of the universe's unfolding physical story. Music, mathematics, love, grief, curiosity all emerge from matter briefly, organizing itself into living minds capable of reflection. The same laws that allow stars to shine also allow consciousness to exist for a while beneath them. But those laws never promised permanence. Viktor Frankl understood this from another direction entirely. After surviving Nazi concentration camps, he argued that meaning is not granted by the universe externally. It is constructed through response, through choice, through the way conscious beings confront suffering and impermanence. A temporary existence does not invalidate experience, it intensifies it. The Stoic philosophers reached similar conclusions nearly 2,000 years earlier. Marcus Aurelius wrote that change is nature's delight. Nothing remains fixed because the universe itself is process. Stars evolve, galaxies merge, even space-time changes shape across billions of years. We are part of that movement, but knowing the universe ends eventually changes the emotional texture of the present. Sunlight feels less ordinary when you understand stellar lifetimes. The night sky becomes less like wallpaper and more like an event already passing away. Every constellation you have ever seen exists during a brief cosmological interval. The galaxies visible through modern telescopes will not always remain observable. The cosmic background radiation carrying evidence of the Big Bang is already fading. We arrived during an unusually bright chapter. Not at the beginning, not near the end, near the peak. The heat death of the universe is separated from us by spans of time so immense that human language barely functions around them. No person alive today will experience even the smallest fraction of those eras. But awareness still matters because it reshapes how we see the moment we inhabit now. The stars are burning. The universe is awake with structure and light. And for a brief interval inside that immense unfolding, you are here to witness it. At the edge of every equation we have followed, another question waits quietly underneath. Not what happens after the universe dies, why there is a universe at all. The philosopher Gottfried Wilhelm Leibniz asked this in 1714 with startling simplicity. Why is there something rather than nothing? More than 3 centuries later, the question remains unanswered, not because humanity ignored it, but because every explanation seems to open into another layer beneath itself. Physics has become extraordinarily powerful at describing behavior. We can calculate how stars evolve. We can measure the age of the cosmos to remarkable precision. We can trace the expansion of space across billions of light years and reconstruct conditions fractions of a second after the Big Bang. But description is not the same as ultimate explanation. General relativity explains how gravity shapes space-time. Quantum mechanics predicts the behavior of particles with astonishing accuracy. The Standard Model organizes the fundamental forces and fields underlying matter. Yet none of these theories tells us why those laws exist instead of different ones, or none at all. Even the constants embedded inside physics appear strangely balanced. Gravity is extraordinarily weak compared to electromagnetism, yet strong enough to form stars and galaxies. The strong nuclear force binds atomic nuclei together with remarkable precision. Small changes in these values could produce a sterile universe with no chemistry, no stable matter, and no long lived stars. This is the fine tuning problem. Some physicists argue that a multiverse solves it naturally. If countless universes exist with different constants, then at least a few would accidentally permit complexity and observers. We would inevitably find ourselves inside one of those rare habitable universes because no conscious beings could exist elsewhere to ask the question. But that explanation moves the mystery outward rather than removing it. Why does the multiverse exist? Why does it generate laws at all? Why does mathematics describe reality so effectively? Each answer produces another why beneath it, descending further into foundations we still cannot see clearly. Other thinkers propose that the laws of physics may someday emerge from a deeper necessity, a framework in which the universe could not have been otherwise. Others suspect that the question itself may sit partly outside science, not because it is unimportant, but because science studies relationships within existence rather than the origin of existence itself. Physics does not currently decide between these possibilities. It leaves the door open. And then there is the strange fact of consciousness itself. Matter organized into atoms, atoms into cells, cells into nervous systems, and eventually into minds capable of contemplating cosmic origins and endings. The universe became aware enough to study its own structure through temporary biological observers orbiting an ordinary star. You are one of those observers. That can feel either inevitable or miraculous. Given enough universes, perhaps awareness was statistically unavoidable somewhere. Or perhaps the emergence of conscious beings capable of asking these questions is among the rarest events in all of cosmic history. Physics remains silent on which interpretation is correct. The universe never directly answers why existence exists. It simply continues presenting the question, written across expansion and entropy, across light and darkness, across every star that burns briefly against the cold. Before any final conclusion, the scale softens, not into comfort, but into perspective. Everything that forms you began long before Earth existed. The carbon in your cells was forged in the cores of ancient stars. Those stars lived, burned, and died billions of years before the solar system condensed from their remnants. The iron circulating in your blood was assembled in the violent deaths of massive stars scattered across interstellar space in supernova explosions that briefly outshone entire galaxies. Even the simplest elements in you carry deeper time. The hydrogen atoms and water molecules inside your body are not newly created. Many formed in the earliest minutes of the universe, when it was still a hot, dense plasma expanding outward from the Big Bang. They are approximately 13.8 billion years old, unchanged in identity, while the cosmos evolved around them. You are not separate from this history. You are a configuration of it, a temporary pattern in matter that has existed in other forms for the entire lifetime of the universe, a local reduction in entropy briefly maintained within a larger trend toward dispersion and equilibrium. Structure emerging inside a system that naturally moves toward disorder. From the Big Bang to this moment, the universe has changed state repeatedly. Simple particles became atoms, atoms became stars, stars became galaxies, and within one of those galaxies, a planet formed conditions stable enough for chemistry, biology, and eventually thought. The same physics that builds stars also builds observers. In 13.8 billion years, matter evolved into something capable of understanding its own evolution. Physics, cosmology, thermodynamics, and quantum theory are not external to this process. They are products of it, descriptions written by structures made of the very thing they describe. Carl Sagan captured this idea with precision when he said, "We are a way for the cosmos to know itself, not as metaphor, but as observation." The universe organizes matter into temporary systems that can reflect on the universe itself. But that capacity is not permanent. The same conditions that allow stars to shine also allow minds to form. Both depend on gradients of energy, differences in temperature, and flows of usable work. As entropy increases, those gradients disappear. Stars extinguish. Complexity fades. Consciousness, as far as physics can currently describe it, loses its supporting conditions. In the far future, after stars die and black holes evaporate, there will be no structures capable of thought, no observers to record time, no memory of galaxies or light or experience, only particles drifting in expanding space without arrangement or awareness, which means something precise and strange. The universe is not always known. It is known only during a narrow interval when complexity exists long enough to support observation. That interval is the Stelliferous Era. It is brief on cosmic scales, already passing. You are inside it now. Every thought, every measurement, every question about endings and beginnings is occurring during the only period in which such questions can be asked and understood. Not outside it, not before it, not after it, right here, right now. The universe, for a moment, is looking at itself through you. We return, one final time, to the question that has followed everything before it. What comes next? The simplest answer physics can currently give is also the most constrained. After the universe dies in heat death, there is the dark era, a state of maximum entropy, a cosmos still expanding, still existing in a technical sense, but with no usable energy gradients to drive change, no structures large enough to evolve into anything new, no clear separation between past and future in any practical sense. But even this description begins to stretch language, because after assumes time still behaves in a familiar way. In a universe that has reached equilibrium, time becomes indistinct, not because it vanishes, but because nothing happens that can define its passage. What follows the dark era is not something physics can currently describe with certainty. It may be Poincare recurrence, where fluctuations over inconceivably long timescales reconstruct states resembling earlier configurations. It may be quantum tunneling into entirely new vacuum states. It may be the birth of a new universe through processes we do not yet understand. Or it may be that the question itself stops being meaningful because there is no longer a valid distinction between one moment and another. We do not know, and that uncertainty is not a gap to be casually filled. It is the boundary of current understanding. But what we do know is already immense. The universe began in a hot, dense, rapidly expanding state. Over billions of years, it cooled and structured itself. Matter organized into atoms, atoms into stars, stars into galaxies. Planets formed from the remnants of stellar evolution. On at least one of those planets, chemistry became biology. Biology became cognition. Cognition became reflection. In a universe governed by simple physical laws, complexity emerged, not because it had to, but because it could. The second law of thermodynamics does not require stars or carbon or consciousness. It only requires that entropy increases. A universe could satisfy that law without ever producing anything more complex than diffuse particles spreading into emptiness. Ours did not remain simple. It developed structure. It produced light. It allowed matter to assemble into beings capable of asking what all of it means. That fact remains true regardless of what the far future holds. Stars will end, black holes will evaporate, space will continue expanding toward cold equilibrium. But none of that erases the brief interval in which the universe became dynamic, complex, and observable. Whatever comes after cannot undo what came before. The universe was not required to become anything in particular, yet it became a place where change, structure, and awareness could arise, where physical law gave rise to experience, where matter organized itself into observers, and observers learned to understand matter. And in this moment, that process is still unfolding. You are part of it, a temporary structure in a long cosmic evolution, a way for the universe to remain aware of itself during the only phase in which awareness is possible. Whatever comes next, if anything comes next, belongs to a scale of physics and time we may never access. But that does not diminish this interval, because this interval happened, and while it lasts, the universe is still, quietly, asking itself questions through you.